All right, welcome to this intensive revision explainer. Think of this as your absolute ultimate boot camp for conquering those high-priority A-level chemistry topics, and more importantly, dodging those notoriously common exam traps. Whether you're feeling a little overwhelmed by reaction mechanisms right now, or maybe you just need to sharpen up your data analysis skills, you're exactly where you need to be. We're going to break down the complex patterns, visually map out the micro-worlds of bonding, and highlight exactly where examiners are waiting to catch you out. So let's get right into it. Here's a quick look at our roadmap for today. First, mastering periodic table patterns. Second, visualizing complex chemical bonding. Third, organic chemistry reaction mechanisms. And fourth, acing your practical assessments. Kicking things off with Section 1, Mastering Periodic Table Patterns, where we'll unlock those big macro trends. So the absolutely crucial takeaway here is that periodicity isn't just some random assortment of facts you have to painstakingly memorize. It's really not. It's a predictable, repeating rhythm across periods, kind of like moving from sodium all the way across to argon. Once you understand the underlying why of this rhythm, you honestly don't need to memorize every single data point. You just follow the trend. For example, take a look at the general increase in first ionization energy across a period. If you follow the trend, you literally see it climbing steadily from lithium all the way up to neon. Why does it do that? Well, because as you go across a period, the nuclear charge increases. You're adding more protons. But the electron you're trying to remove comes from the exact same shell. Since distance and shielding remain reasonably constant, that overall force of attraction just pulls tighter. It simply takes a lot more energy to rip that electron away. But okay, here's the trap. Examiners absolutely love testing the exceptions to this rule. I mean, they're practically waiting with their red pens. Notice that rapid drop between the last element in one period and the first in the next, like going from helium down to lithium? Why the sudden plunge? Well, lithium's outer electron enters a brand new quantum shell further from the nucleus, and that vastly outweighs the increased nuclear charge. Even sneakier is the slight drop between group 2 and group 13. Look at beryllium and boron. Boron has one more proton, sure, but its fifth electron goes into the 2p subshell, which is just slightly further away than beryllium's 2s subshell. That tiny increase in distance means less attraction, causing a slight dip in energy. You absolutely have to lock those exceptions into your memory. Moving right along to Section 2, Visualizing Complex Chemical Bonding at the Micro Level. You know, what's truly fascinating here is how dot and cross diagrams explicitly map out those shared outer shell electrons. You can see exactly which atom every single electron comes from. When two nonmetal atoms combine, they share one or more pairs of electrons to fill those outer shells. And using a dot for one atom's electrons and a cross for the others isn't just busywork. It's actually a really critical visual accounting system. Whether it's the elegant simplicity of a hydrogen molecule or the shared structure of ethane, this visual mapping proves exactly how the atoms satisfy their energy levels. Now, you've got to lock down the distinct difference here to avoid mixing up your terminology on test day. Let's take a chlorine molecule, for instance. It shares one pair of electrons right smack in the middle. That is your bond pair, which is often represented by a single structural line. But don't forget the rest. Each chlorine atom still has 3 pairs of outer shell electrons just minding their own business, not bonding at all. Those are your lone pairs. Identifying bond pairs versus lone pairs is step 1 in predicting a molecule's 3D shape, making it an absolutely foundational skill. Shifting gears now into Section 3, Organic Chemistry Reaction Mechanisms and Electron Dynamics. First up in our back-to-back definitions, we have electrophiles. The name literally translates to electron-loving. Because they're deficient in electrons, they are incredibly eager to accept an electron pair from another species. And when they do, they form a brand new covalent bond. You're going to constantly see these driving addition reactions in organic chemistry. On the flip side, nucleophiles are your electron-rich donors. They carry either a full or a partial negative charge, actively seeking out a positive center to donate their pair of electrons to. Keeping these two completely straight, electrophiles as acceptors, nucleophiles as donors, is basically non-negotiable for accurately mapping reaction mechanisms with your curly arrows. If you mix up who's donating and who's accepting, your entire mechanism is going to be mapped backwards. So, a perfect example of an electrophile that examiners heavily test is the carbocation. That's an intermediate structure with a positively charged carbon atom. But here's the thing. Not all carbocations are created equal, and their stability totally dictates your reaction products. The golden rule: the more alkyl groups adjacent to the positively charged carbon, the more stable it is. Notice the tertiary carbocation. With 3 carbon groups attached to the center, it's significantly more favored to form than a secondary or primary one. That stability difference is exactly why you get major and minor products in addition reactions. Beyond the mechanisms themselves, you really need to be able to instantly categorize what type of reaction is occurring. Memorize this rapid-fire list. Addition creates a single product. Elimination pulls a small molecule out. Condensation is a two-step dance of addition and then elimination. Substitution swaps parts out. Hydrolysis uses water to break a molecule apart. And finally, oxidation is usually spotted by a change in oxygen or hydrogen atoms. Recognizing instantly that, say, hydrolysis breaks down a halogenoalkane will save you precious minutes when you're identifying reaction conditions. Finally, we hit Section 4, acing your practical assessments, covering labs and data. All right, listen up because here is a massive pitfall alert. Writing clear instead of colorless is a classic mistake that will immediately cost you observation marks. In everyday language, sure, we use them interchangeably, but in chemistry, they are completely different things. Clear just means transparent, light passes through it. A solution of copper 2 sulfate is perfectly clear, but it is undeniably blue. If a solution looks like water, transparent and without color, you must write colorless. Never, ever use clear to describe a lack of color. Another area where precision is just ruthlessly tested is in multi-step calculations, specifically lattice energy using Born-Haber cycles. Honestly, students almost always forget steps 3 and 4 here. Keep this exact mental checklist handy. Yes, you remember the enthalpy of formation and atomization, but did you convert all atoms into ions with the correct charge? And critically, did you account for how many moles of each ion are in 1 mole of the compound? Think about it. If you have magnesium chloride, you have 2 moles of chloride ions. You've got to multiply those energy values by 2. Missing that multiplier is the #1 reason students drop the final calculation mark. So, as we wrap up this explainer today, I really want you to honestly evaluate your readiness. Challenge yourself to confront these exact pitfalls right now. If you sat down with a practice paper today, would you catch yourself before writing clear? Would you double-check your mole ratios and correctly map out those nucleophile electron pairs? Keep these visual frameworks in your head, and you won't just memorize the chemistry, you'll truly master the mechanics behind it. The real question is, which of these traps were you about to fall into?